I'm
I'm
mic'd here.
introducing you.
Okay.
No, you have that. You're mic'd.
And they'll be able to see.
Yeah, and on Zoom and YouTube
Okay, perfect.
and Instagram. No Instagram. All right. Should I ring the bell?
Yes.
It's just weird. All right. All right, thank you all for coming today. It's my pleasure to introduce our speaker, Jon Warrick, who's going to steal a pen as a memento. Oh, you got the mug already, even before the talk.
Yeah, I know.
Well, that's good. All right, so some of you already know Jon. He actually was here about 5 years ago to give a talk. Is that right, Jon? About that. Yeah, you got it. Okay.
Sorry.
No worries. So Jon Warrick, a PhD, is a research geologist at U.S. Geological Survey in Santa Cruz, California. Jon received his PhD from the University of California, Santa Barbara in 2002, and has authored or co-authored over 90 peer-reviewed science articles, reports, and book chapters. His research focuses on coastal change and the movement of sediments from rivers to the sea. Jon has led efforts to characterize the outcome of the massive dam removal project on the Elwha River of Washington. And actually, you came here for that talk when that happened. It was pretty freaking cool. Yeah. And so this massive dam removal project on the Elwha River of Washington in collaboration with the Lower Elwha Klallam Tribe, federal agency, and several universities. Recently, Dr. Warrick has led the USGS Remote Sensing Coastal Change Project, which has collected and interpreted remote sensing data to better understand changes into the U.S. coast from wildfires, floods, landslides, hurricane, and other storm events. Fun stuff, huh? Dr. Warrick and his work has been featured in multiple media outlets, including the New York Times, the Washington Post, the Los Angeles Times, KQED Forum, Outside Magazine, and the nationally broadcast CBS Evening News. And he was recently featured in a short video entitled Science of Surfing, where he surfed. No, he didn't surf.
I actually,
Yeah.
My daughter's in it too.
Oh, is she?
Yeah.
Was she surfing?
Yeah, in fact, I surf past her and we high five.
Oh, that's really
We
cool.
have to get to like minute 4 or
So
5.
just check him out on YouTube. Jon Warrick, the surfer. All right. Thank you for coming. All right.
Appreciate it. Good to see you. Thanks so much. Today, I'm going to talk about measuring shoreline and shoreline change with satellites. And that's probably about as far as away from the beach as you'd like to get to try to measure change. But I'm going to show you today that we can do it, and we can do it reasonably well. And there are certainly some challenges with it, but it works. And it's kind of redefining the ways that we're doing science in the coastal zone. So today I'll focus on these questions. And the first is, can you dim it a little bit? How useful are the satellite-derived shoreline data? I'll show you in just a second. There's a lot of new data coming out, and it's accessible if you want to do a project on it. The data are available. There's data for most of the world right now that you could download and start playing with if you're interested. And then what can these data tell us about change? That's even worse, my friend.
Number 5, Alana.
5? I'm hearing 5. Well, one of the reasons we're interested in satellite data is because it can fill some important gaps in our understanding and the data that we have available to us. And that was shown in Sean's recent paper. This is Sean Vatusek's recent paper in Coastal Futures. And if you look at the graph on the right, the green box is what we sort of think where our satellites can perform reasonably well. And you can see that it sort of expands somewhat the temporal and spatial scales that we are able to observe things. And so that's in itself an interesting thing to think about, that there's a lot of new opportunities to see things at different scales temporally and spatially. And we've seen that there's a lot of satellites that are becoming available. This is somewhat dated. This is from Killian Voss's paper a number of years ago. But the idea in it is that there's a lot of new data and a lot of new satellites being launched, and some of them are publicly available data, and some of them are these commercial satellites on the bottom, but we have more and more opportunity to make these types of measurements if they work reasonably well. Just a quick sort of background if you're not a satellite person. Satellites provide us generally with two-dimensional data, and I just want to highlight the fact that those will provide a sort of unique opportunities, but also some limitations, especially when we think of, I play a lot with 3D data, and so the data on the right are 3D point clouds taken from airplane aerial imagery that we collect in the USGS, and this is Rincon Point down by Santa Barbara. And you can see, in the 2D data, you can see all kinds of features, but what you can't see is you can't measure maybe how steep this beach is over here. You can with the 3D data, but not in the 2D data. You can, and you can't see this rack line. You couldn't measure the elevation that occurs on in the 2D data. But what you can see is sort of where is this wet-dry line, where is the white water, all kinds of features like that. So another example more locally, just down south of us, in bluffs and cliffs, 2D data can be really useful, but 3D data really is where it's at, because you can see the cliff edge or the bluff edge and start seeing things like, failures and overhangs and all kinds of things like that in the 3D data. So again, 2D data is extremely useful, but doesn't have all the properties of 3D data that we sometimes like and get used to. One of the neat things about a lot of the satellites is that they include infrared bands, and infrared is really useful for determining where water is, and that's because infrared light is absorbed quite readily by water, and it's reflected by land. And so this is just an example from a wonderful country that we were talking about earlier with my friend, where you can see you can see how well it distinguishes water and land, and that's because it's using a sort of a ratio of infrared light and visible light, green light, and from that you can see where the water is fairly readily. So we use these infrared bands, these infrared information a lot in determining where shorelines are. So there's basically two approaches. So now I'm jumping into sort of how this is done. How do we measure shorelines from satellites? And there's basically two methods. And one takes composite images, or generates composite images from a series of available imagery. And I'll show you an example of that. That's being done by the Australian government to map their shorelines. And basically what happens there is you take maybe a year of data and you cull the data to the imagery that's most useful to you, and then you do something to it. Here they're just making a mean annual image, and then you measure the shoreline in that. So that's one approach. Again, compositing images. And another is you take the other method, and this is the method that we use in our analyses, is you take an image, and for each image that's available to you, you try to map the shoreline in it the best you can with the data available. And then you end up with a lot more imagery over time. And again, I'll show you that in a second. So these are data from Australia, and the Australian government has measured their shorelines for every year available in the Landsat database. So that's 1984 to the present. And what they do is that composite analysis where they composite every image that's available for a certain year from Landsat, and then they derive where the shoreline is during that year, and then they produce maps such as these. And you can watch this, and you can actually go this is all available. If you're interested in this, you can both download these data if you want to play with them for a class or in your own research. And you can also just go on the website and just watch your favorite Australian coastline changing. It's kind of fun. The other approach is that individual analysis. And what's really neat is that it produces time series of data. And so I'll show you a lot of graphs like in the lower left here. And so this is for just on the other side of the harbor here, over in Moss Landing, on the north side of Moss Landing. This is a time series of shoreline position since 1984. And so you can see it sort of wiggles a lot. It goes up and down and up and down and up and down. Those are those annual cycles of accretion and erosion, and accretion and erosion. Erosion back and the beach accreting down. And so those are annual cycles. And you can also see there's some big wiggles in it. There's some interesting wiggles in it. We'll talk about all those things in a little bit. But you can also see there's quite a bit of noise, and I'll talk about that in a little bit too. And you get these type of data because, again, we're looking at every image and we're measuring a shoreline in each image. And then those shorelines are mapped out. And what we end up doing is analyzing those shorelines at transects. So cross-shore transect. You can see some of these lines here. Those are all cross-shore transects. And for each one of those, we intercept the series of shorelines that have been mapped, and we tidally correct them. And so we try to handle the fact that the water level's up in some of the imagery and it's down in other imagery. We try to normalize that with a slope measurement, and we end up with measurements like this. I could talk for an hour about the process, but I'm going to skip over it. But basically, it uses a classification scheme using the RGB and infrared light or bands in the satellite imagery, and a machine learning classification of that image, distinguishing water, like whitewater, sand, and other. So we could talk, if you're interested in that, I could talk your ear off about it. It's kind of fun, but I'll skip over it. If you're interested in it, it's all in Killian's paper from 1990, or from 2019. We at the USGS are working on improving some of those. We're actually working with Killian on some of those tools, and so we have some new techniques that have been introduced. We call that COSEG, because it does a lot of segmentation of the imagery to help us better see the shorelines in it. We have a recent publication on that, and there's actually an online code that you can download and play with and use to more efficiently download imagery and derive shorelines. If you're interested in doing this, yes, take a picture. COSEG, that's your spot. All the code is available. It's all in Python. You should be able to run it and use it for a class or whatever, your own research if you're interested. Sharon is the master programmer behind it, and Dan is one of our coastal scientists who's helped come up with the overall sort of scheme of how this works. We're also developing what we call SDS tools for satellite-derived shoreline tools. This is sort of a small database. There's a Git site that has some of the tools we've introduced, but our idea is we're going to make a tool shed, or at least a toolbox, where you can go and use various tools to come up with monthly averages or all kinds of different analyses that I'll share with you to analyze the data. So there's sort of a standard toolbox that you can apply to these. So check that out too, again, if you're interested. So let's get to sort of some of the basics of what's going on with our individual satellite image analysis. And so this is, anyone know where this is? I've turned it. So yes, it's right. Yep, Carmel Beach and Monastery Beach. Very good. And I have turned it on its edge just so it fits in the imagery. So north is up, or north is to the left. I apologize for that. And so if you think about where the water line is in any imagery, let me back up. So the technique that we use, it does a reasonable job at seeing where the water line is. And that's because primarily it uses that those infrared bands to see water-land differences, okay? So where the water line is a function of a number of things. It's a function of tides, beach slope, but also wave swash processes, right? And if we were to measure that instantaneous water line in this image, I would probably do something like that. The thing is, if we came back 5 seconds later, those waves may have swashed, in a different pattern. And so immediately, hopefully you can see that this technique, a waterline technique, is not perfect, one, and two, it's dependent on the amount of swash going on up and down that beach, and sort of the sort of random time that you took that image. So you could have taken the image could have been collected when the waves are all down rushing, right, and the beach was very exposed, or you might have got an image when a big set had come through and just washed up the beach, right? That sort of variability in the imagery introduces a lot of noise, and you're going to see that in a second. These data are noisy, and so I showed you these data before, and the reason you can sort of see the noise is, if you look at some of these areas, you can see quite a bit of variability in them. If you compare the measurements that we get out of satellites and ground-based measurements of where the mean high water or the mean sea level shoreline is, generally we get about a standard deviation of 15 meters in the horizontal. That's a lot. Is this room 15 meters? How big is this room, right? That's about, it's about a pixel size in the pan-sharpened imagery we use. And it's also, probably a swash zone or so, right? So it's about that scale. So you might say, wow, this is a really poor tool in terms of measuring where the shoreline is. And it is on an individual basis. And so one question we like to ask ourselves a lot is, how useful are noisy data? And I'll use this example from Wikipedia in showing this sculpture. And if you see that line across the left-hand side, that is the series of brightness values for that line is shown in the bottom panel. And you can see there across on the left-hand panel, where you see that head really nice, you can see that this pattern is dark and then light, and it captures, and here we're showing signal to noise ratio. So the signal is the amplitude of that dark to light signal, and the noise, the variance, is how much variability. And basically we added, but someone added noise to this image as you go to the right. And that signal to noise ratio gets pretty bad, down to 1 here. And my question to you is, when do you stop seeing that head? And my answer is, I still kind of see it over here on the right. Kinda, right? Is it there or not? Is it a head? Yeah. Is this a head? Sure, right? I mean, what kind of hair? Where's the ear? I don't know. It's probably in there, but do you see it? No. I mean, can you tell, is that hair straight or curly? No, but you can kind of make out the head. The idea being there's still information, even though the signal to noise ratio is very high. Look at this data, it looks like crud, right? There's still some information in there that potentially could be interpreted. Certainly as you get into these less noisy realms. But the idea being that we still can see some of those patterns even in noisy data. And there's things that we do, and there's a whole fields of science that look into this, is what do you do with noisy data, and how can are there signal processing techniques to actually bring information out, right? And there's generally 2 types of ways that you can do that, and those are shown here. And so what this shows is, up in the upper left is an original noisy scan. There's a signal in the middle of the scan, and then there's noise. And so the first thing you can do is you can scan that thing multiple times, and each time just average your results. So you just scan it and scan it again, scan it again, scan it again, scan it again, right? This is a very common technique in all kinds of sciences, from astronomy to, I'm sure, maybe the stuff you do in chemistry. Like you think you measure something over and over again, and as you do it, that noise goes down because you're introducing multiple scans and you're averaging them. So you can think of, if you look at something and you image it several times, then you can actually see that the signal to noise goes from 4 to 11 in these data. Another way you can treat a data set if you only have a single scan is you can do some sort of moving average. And so here you can see the original data, and then you increase that, the number of data points that you're smoothing over, and you can see that the signal-to-noise ratio increases. Other things happen when you low-pass filter or you do a moving average, including sometimes you wipe out the amplitude of the signal. But it can be an effective tool. And these are sort of the two general ideas that we take to our noisy satellite data to try to distill out some of the signals that are in the data. And just as an example of this, this is from another of Killian Voss's works, looking at data from Ocean Beach, San Francisco, and from Australia, looking at satellite imagery in the orangey colors and some in situ beach data in the blue colors, showing, they have the same kind of patterns here, and these are now monthly data. And the nice thing that he shows is that the standard deviation has gone from something like 15, 16 meters now down to 11.6 meters. So that noise has been decreased because of just simple monthly averaging. And so just an example of how if you treat the data in a certain manner here, time averaging, you can reduce some of the noise in it. The question is monthly data good enough for you? That's a question you might ask yourself if you were doing science with the data. Is it adequate for the things we're trying to do? For us, a lot of times, monthly data is. Okay, so let's now apply this to the real world and go look at the California coast, and see how useful these satellite-derived shorelines are. And I'm going to focus on a couple patterns that we can see in the data for California. And that will be trends, and I'll go over that really fast, events, and then seasonal cycles. And I'll spend most of my time talking about seasonal cycles in the shoreline, because it's a new paper and it's kind of fun. And so if you go to the COSAT database, so COSAT is something that we funded with the University of New South Wales. It's Killian Voss's work went into creating these types of measurements for much of the Pacific Rim and certain parts of the rest of the world. You can just go look at the trend data in there. And so for each transect, there are trends computed from them. And I'm showing one of those time series. So again, from 1984, when Landsat, the Landsat data we use, Landsat 5 and onward, started, and then up to almost the present here. And so for each of these transects, there's a slope. And you can see, this is in Southern California up by Dana Point. There's been quite a bit of erosion, and down in sort of southern San Clemente, San Onofre area, there's been quite a bit of erosion over time. And down here, it's on the order of almost a meter per year for the last almost 40 years. That's quite significant. And what's really nice is you can look at sort of spatial scales of this, and people are starting to use this to think about convergence, divergence of sediment, erosional places and places where sediment is accumulating along the coast. And of course, these are really relevant issues because there are communities that are wondering where their sand is going and what they can do about it. Now, whereas trends are certainly can be computed in these data, I would suggest that there's probably a little more information we can pull out of these. And when I look at these data, I see that there seems to be at least 3 different sort of eras in the data. That we have this sort of late 80s, early 90s where the beaches were eroding quite quickly. Something happened in the 90s. These beaches jumped back out, and then they've been eroding at a slower rate since then. And I think in terms of management and an understanding for why these beaches are working in the way they do, I think it's important to think about what's going on here. What happened here? Was that a year that floods brought a lot of new sediment into this beach? Is that a sediment wave moving down the beach? Why would the beach function in this manner, and what does it mean in terms of the long-term evolution of this beach, and can we expect those in the future, et cetera. And so I think in terms of the data we have, I think it's useful not only to think about trends, but some of the time-dependent trends in the data. And that's why I'm going to jump into the second section, which is events. So one of the really neat things about these data is they can tell us a lot about events. And what I mean by that is sort of in the engineering framework, the unsteady sort of nature of coastal change, in other words, the time dependence in that. And here's just some data we included in a recent paper showing the Santa Clara River in Southern California, and how the shoreline there, bumped way out and bumped way out and bumped way out in these years after big floods. And what's interesting is if you go, and so the river mouth is here. If you go down and look at a transect, is it a kilometer or 2 kilometers? It's 2 kilometers away from the river mouth. You can see that signal is sort of muted, and you can see about 60, 70 meters of accretion down there as this new sediment wave is slowly passing, but certainly not sort of at these punctuated, in this punctuated manner. So these events here, they're floods that introduce new sediment to the coast, can result in very interesting changes that occur down coast. We recently looked at this in the Big Sur coast, where a paper we published a couple years ago looked at the delivery of new sediment to the coast following a wildfire and a very wet winter, which washed a tremendous amount of new sand to the coast. And just to show some of the imagery, I won't show the time series, I'll spare you some of those details, but showing, this is at the Big Sur River mouth, showing a fairly narrow beach before the floods washed that new sediment in, and then we can see a much wider beach and that sand moving down coast. Again, I won't show you all the data, but just to show that these satellite imagery using this COSAT method, these are all either Landsat or Sentinel-2 imagery. We're able to pick up these changes. And we came up with this conceptual model from that paper about how after these big events, we have lots of new sediment being washed into the river mouth region, and then that sand moving down coast over the following years. And then, the location of that sand in any one year is related to the direction and the size of the waves. And so there's some interesting patterns in the satellite imagery. I'd have no time to talk about all that. Invite me back, I could talk about it another time. But just to show that we're able to see these types of events with Landsat data. And this was, this small-ish beach. I don't know if anyone's been to the Big Sur River mouth. Yeah, it's, has these narrow, neat little beaches. And what this told us is that, gosh, if we can do this here, we could do it almost anywhere. We could look at beaches up and down the coast and see if we see events like this. And so we started up on the north side of California, and we got stuck right away because the Klamath has some really cool stuff going on in it. Not only is it a beautiful landscape, but there's a fantastic sediment transport study that we were able to do, and some really neat processes going on here. And so the Klamath, you may have heard of the recent dam removals, right? This is the Klamath River, Northern California, fantastic place just north of Eureka, up near the Oregon border. There's a littoral cell there that basically is understood to start near the Klamath River mouth, and mineralogy of the sand suggests that this sand is moving to the south. And it's a rugged coast. There's all kinds of neat stuff there. Well, we started, again, we did that study in Big Sur, and we thought, let's go look at something else. And I thought, I'm going to look at the whole entire state. I'm going to find these events all up and down the state. And we go up this Klamath, and we see data like this. And I said, oh, crud, we're going to have to write a paper on this. And so we got stuck, and I have yet to do the whole entire state for events. But we do have a really neat story about this large sediment wave that passed through this littoral cell. And so what you're seeing here are those shoreline data for various transects. I've only included a few. You can see they're color-coded on the map here. Purple in the north at the Klamath River mouth, and then as you go further south, the colors change like that. And you can see, like up here in this rocky reach just south of the Klamath River mouth, we had a sediment wave. We have this, the beach got 200 meters wider. 200 meters, right? That's 2 trips around the track and field, right? That's a lot. That's not 2 times. That's 800 meters. What am I talking about? That's halfway around that dang field, right? So, sorry. Right. That would have been a half mile. That would have been really cool. No, so this is 200 meters, and then it receded, and that occurred over about a decade, right? And as you go further south, you can see that wave entering and that waveform changing. It's getting sort of elongated. And as you get down into this area called Gold Bluffs Beach, which is quite near where they filmed Return of the Jedi, the Ewoks where they live, on the ferns and stuff like that. I'm dating myself, sorry. That's down in here, and you can see that sediment wave kind of coming in and out, and it's taking many decades. And then you get to the farthest south, you don't really see much, maybe a little bit of accretion here. I mean, it's 50 meters, I guess more than a little bit, but nothing like what you're seeing in here. And if you look spatially, it looks like this. So this is a map. So time is on the x-axis and distance along the coast from the Klamath River mouth down to the Rocky Point and south. And the color shows basically the change from the initial 2 years. And so you can see blue is accretion and red is erosion. And so I didn't point this out earlier, but the Klamath River mouth, the bar was quite seaward, and then it eroded back. And as it eroded back, this wave of sediment entered, and you can see it sort of progressing and sort of just smashing into Gold Bluffs Beach here and residing there, where we have 150 meters of accretion occurring over the last 40 years. 150 meters of accretion occurring over the last 40 years. It's quite a wide beach there, and it got much wider. And so we wrote a whole paper on this. Again, I won't go into all the details. There's lots of cool stuff going on down here, too, I can't talk about. There's actually another maybe a small sediment wave that came in there. Lots of cool stuff going on. The take-home is that Gold Bluffs Beach, and we actually used historical maps and historical records to find out and document that Gold Bluffs Beach, where all this sand is now parked, used to be impassable at high tide. It had a really steep cliff, and you used to not be able to pass it. At low tide, people would go out there and run and clam or something, then at high tide, they'd run back. Okay? This beach is 600 to 800 meters wide now. And it's prime elk habitat. The elk love to come down there and hang out. And there's a couple there's a nice campground. Go check it out. It's a really neat place. And our understanding is that this has all occurred through probably a series of those sediment waves in the last 150, 200 years. This has all been accreted. And the best understanding for why that's happened is because of the placer mining, the gold mining, and the deforestation that's occurred in the watershed up in the Klamath. That's a whole nother story, but the take-home is this beach wasn't here 200 years ago. In fact, the Yurok tribal names for this beach is the place. It can be translated as the place that thumps. And what they meant by that is that's where the waves come up and thump against the cliffs, right? It's the place that thumps. I can tell you, these waves don't thump on that cliff anymore. In fact, that cliff is overridden by all kinds of vegetation. So a really interesting story here about not only this big sediment wave that came through, but also landscape change on fairly phenomenal scales. Okay, so those are events. The last thing I'm going to talk about is seasonality. And so this is the third type of thing we can see with satellite data. And so if you go way back in the literature, Francis Shepard wrote this sort of seminal report back in 1950 based on data collected in the 30s and 40s. This was part of that World War II crew that was down at Scripps doing all their measurements, the good old days. And one of the things that Francis looked at a lot was beach seasonality. And so you may have seen this figure. This is sort of one of those repetitive figures showing a beach profile. So if you were to look at it, slice through it, showing the cut and fill that occurred sort of winter, summer, right? And that recurring pattern of, it's full of sand, it's gone. It's full of sand, back and forth, year after year after year. And this is one of the sort of characteristic features of California beaches. Hopefully you've learned about that maybe a little bit in your classes. And of course, Bascom, Waves and Beaches Bascom wrote a seminal report on this characteristics of natural beaches. And he was probably the first person who called these things the summer profile and the winter profile. So this is, the beach, wide beach in the summer and the narrow beach in the winter. And right, this figure is figure 1, and he kind of defines these terms, again, way back in the 50s. And of course, we've seen a lot of work on this type of thing from a whole host of folks. Here's Doug Inman's work, Melissa Yates' work, which is really foundational for understanding the waves' influence on this. And so the general understanding is that, winter waves are bigger, summer waves are smaller, and we have these cycles that are induced on the beach because of the erosion and accretion that occurs, right? Hopefully this is not all new to you, but it's sort of one of the foundations of sort of beach morphodynamics. And in fact, if you go into Google and use your AI thing, you just type in beach seasonality, it'll spit out this thing, and it says that beaches undergo seasonal changes. I can't do it in AI voice, I'm sorry. But in variation in wind and wave energy and wind in summer, during the summer, beaches are wider. In the winter, beaches are narrower. So, basically, Google has scraped all the information out there, digital, and come up with this as the main answer for beach seasonality. And then, again, summer, wide, winter, narrow. And so this is a lot of data, but this comes from one of Melissa's papers a number of years ago, where she was looking at sort of those changes in beaches in San Diego, on the southern end of our state. And she looked at 3 different LiDAR surveys. I'm just going to have you focus in on this middle panel. And what she's showing here is the sea level change. So in other words, where the beach intercepts mean sea level, and how much it changed during a certain winter, and then the next summer. And so this is erosion on this side of the 0 line. So here she's showing winter erosion followed by summer accretion. This is sort of that pattern, right? And so in general, she saw that here too. But what's really interesting to me is that there are places where she didn't see that. And in fact, there's a place up here where it's opposite. Summer eroded and winter. Wait a minute, Google AI didn't tell me about this. Wait, this in the summer it eroded, and Melissa doesn't talk about this. The paper is focused on other things, but this is one of the first pieces of evidence I found that was like, wait a minute, something different might be happening here. Is this sort of winter narrow, summer wide beach condition universal or not in California? And so we're going to ask the question, do these shorelines exhibit seasonal cycles, and do they vary in magnitude and timing, especially? And so the cool thing is we have all this satellite data now that we can distill, and I have no time to talk about this, but basically we're using a couple different processes to take records from almost 8,000 transects and distill them into seasonal records. And I'll show you the time series decomposition technique we use here in a second. In fact, that second is now gone, and we're going to look at that technique. And so the technique one of the techniques that we use to look into this is called the seasonal trend decomposition with Loess by Cleveland et al. This is a really popular technique in economics and a lot of things where you're looking at how much do people buy or fly, or how often do they fly, or and there's all kinds of seasonality and economic numbers and stuff like that. It's also used, and I think in ecology quite a bit. Coastal scientists generally don't use it. And one of the cool things is that because we've never really had the data to do it, and so like we're kind of making this up as we go in some ways, but it's also really fun because that means we can apply some new techniques and think about how they work. So let me show you what this does. So what we do have here is just one of those transects. This is in Pismo Beach down south. This just shows the raw data that we got out of the satellites. You can see that it's, it's kind of noisy and it wiggles around, et cetera. So the first thing we do to this is we make it into a regular interval of data. So here we have monthly medians positions. And you can see, again, it wiggles around. There's some annual cycles. They kind of are lower here and maybe more amplified here. Some of the bigger erosional winters I've shown in yellow. And then from that, we measure a time-dependent trend, which is shown there with the red line, and then we remove that to make this detrended time series. And so again, basically subtracting the trend, again a time-dependent trend from the sort of the raw monthly record results in the detrended data. And then it's fairly simple. What we basically do is compile all the January, all the February, all the March data, and measure statistics from all the January data, have a mean and a median, a standard deviation, a range, all kinds of things. And you can see that this is that sort of average or typical pattern that's replicated here in the brown line. So that brown line is just this median pattern right here. And so, again, that pattern is what we call the typical seasonality pattern for this beach. Obviously, sometimes it's more amplified. Sometimes the timing's a little bit different. Sometimes there's some really weird things going on. But in general, that's sort of the typical or somewhat average condition. And there's a number of things that I'll show you here in a second. The first will be the timing metrics. So you can think about this signal. A couple things we pulled out. One is the month of the sort of the narrowest condition. When is it most eroded? We call that T-min, the time of the minimum sort of typical shoreline position. And then we're going to look at T-max, which is when the beach is generally widest. And here in January, it's generally narrowest. In August, it's generally widest. And you can see it kind of has a seesaw or a sawtooth pattern. It kind of takes more months to accrete and get wide than it does to erode back. The other thing I'll show you here is this sort of the typical shoreline excursion distance. So how far it goes back and forth in general. Here it's on the order of about almost 20 meters. Okay? Again, some winters it's more like 60 meters, but this is more of the typical range. So here are some of the data. And bear with me, this will get meaningful in just a second. Okay, you have to get through this one to get to the next one. So if we look at a histogram of those excursion distances, this is what it looked like. First off, about 10% of the data don't have significant patterns in these. We use two statistical techniques to evaluate that. But 90% of the beach transects in California have seasonal patterns. That's kind of cool. So seasonality exists. 90% of our transects we see seasonality. And the distance that the beach moves on average is anywhere from 5 meters up to almost 60 meters on average. So a wide range, kind of an interesting distribution. That's cool. And the data, the narrowest beach is generally January, but hey, there's a cool distribution here. That's interesting. And the data, the widest beach is August, September. That's consistent with what AI told me, Google AI told me, that's right. So cool, that works. Well, let's look at the geographic pattern of that. So here I'm just showing the exact same data. So this is that excursion distance, how far it wiggles back and forth every year. Note that in Northern California and Central California, it's tens of meters on average. You get to Southern California, it's much less. So the beaches in Southern California wiggle back and forth less than the ones in Central and Northern California. The timing of the narrowest beach is generally January. Whoa, something weird's going on. Okay, and what? Okay, I'm from Southern California, so I can say this. there's something weird down here, right? Southern California is weird. What's going on? Beaches are narrowest in May. Okay, that's whack, right? I don't know what's going on. And there's a wide distribution. And if you look at the time of the widest beaches, why is it widest in all over the map down here, right? Sometimes in the middle of winter it's widest in these Southern California locations. In Central and Northern California, it's widest generally at the end of summer. Again, so Central and Northern California seem typical. Something weird's going on in Southern California. If you look at the data in like heat maps, this is what it looks like. And I'll just point out a couple things. This is shoreline excursion distance, and these are the dates of the narrowest and widest beach. But look how cool, like the Klamath, like everything, it's right about 20 meters of excursion distance. Eureka, this is a really cool pattern here, right? You have a lot more wiggling on the northern end than the southern end. And it's up to twice as much as Klamath. The Lost Coast area, wow, check this out. It doesn't wiggle much, but it's way out of cycle. It's narrowest in the spring. What's going on the Lost Coast? That's a cool place, right? What's going on there? That's totally different. And of course, Southern California is just a pile of noise. It's so crazy. So one of the ways we wanted to look at this is we wanted to try to extract, bear with me because we're really close, we wanted to extract a single metric of that timing. And so what we did is a k-means clustering of all of what we call the standardized shoreline positions. And so what we did is you basically subtract the mean and divide by the standard deviation, and you get these standardized measurements of shoreline position. And then we ran this k-means clustering on it to find the 11 clusters. And I can tell you why, because that's where the peak and the intervariance, which is the external variance. Who does k-means clustering? Anyone? There's a way to figure out how many classes you should pick. We did that. And so these are the classes. And what these show is, like in these blue colors, are the winter narrow beaches. So they're eroded in the winter, and they're widest in the summer. And you can see how these classes, they change as you go through them because some of them are getting later and later in terms of their recovery and erosion cycles. And then there are these warm-colored beaches that are narrow in the summer and wide in the winter. And there's some examples of these over here. And if you could read it, if you really squint, you could see that, this is Salt Creek Beach in Southern California, and there's Newport Beach, and there's all kinds of cool places. Again, I have 8,000 or so transects, so I could bore you to death with it. But this is what those k-means clustered. If you looked across California, you can see that these winter narrow clusters are generally in Northern California. Sort of the later winter clusters are in Central California, and we have a wide distribution in Southern California, including a number that are narrow in the middle of summer. So a real interesting diversity of the timing of seasonality across California. And if you look at like specific beaches, there's some really cool patterns. Like look at Eureka versus 10 Mile versus Point Reyes. They're all sort of oriented towards the northwest. And here, these are colored by the k-means clusters. Again, these are early winter, sort of late winter to spring and summer narrow conditions. And so these, probably what you think. It's cool because like class 1's down here in the south, and then class 2, 3 is here in the middle. But you get to Point Reyes. Oh, and I should say that the size of that point is that excursion distance. What's going on in Point Reyes? Completely different. Point Reyes is oriented in the same direction, but something. Does anyone know what Point Reyes is unique? Who's been to Point Reyes? You ever walked that beach? I can tell you, it is backed by some dunes here, and one of the things is that material is exuding a lot more coarse sediment. So this has a gravel fraction in it. There's a very significant gravel fraction, which may be part of the story. But really cool. Like these beaches, you would think, just from their geography, they should be fairly similar in terms of their seasonality. These two are. That one's not. Taking it home, some of our embayments on the Central Coast, Monterey, Morro, and Pismo. Kind of similar patterns, but look at Monterey Bay. Bigger excursions up here north of Moss Landing, much smaller in the south. Santa Cruz has some summer narrow beaches. I can show you exactly where they are. I live up there. And the kids, I can tell you, all the high school kids know exactly where they are too, because they know where they can go and find a sandy beach all year long, right? They know this pattern. Pismo Beach, why is it the excursion of that beach is really high on the northern end and fairly low in the middles, whereas Morro, it's highest in the middle. Why? I have no clue, but this is really interesting. It's like there's a lot of diversity again in this signal of seasonality. Southern California, oh my gosh, wow, check this out. Like summer narrow conditions up near Malibu, but you get in the South Bay and it's more winter to spring narrow conditions. Newport Beach, Huntington Beach, oh my gosh, it's so red. It's all summer stuff. South Swell, actually, is what's going on there. And then, of course, where all the work was done at Scripps is where these blue dots are. But look at around them. There's a lot of orange, a lot of spring narrow beaches and summer narrow beaches. And if you think about it, why is that occurring? Well, it seems to be occurring for a number of reasons. One is just the pure shoreline orientation. So if you think about these K-means clusters, those groups, these being narrow in early winter to midwinter to spring and summer, just the orientation, the direction that beach is facing is a fundamental characteristic. These are generally pointing more to the northwest, and these more to the southwest to south. That kind of makes sense, especially if you start thinking about the swell that they receive, right? South swell in the summertime from the Southern Ocean and from hurricanes in the Pacific will impact beaches that are more southerly oriented. We've looked at a number of different things like different types of wave conditions. I have little time to talk about this. But here you can just look. This is I'll show you this one. This kind of shows what I was just talking about. So this is what we call this the wave direction seasonality. So we use the CDIP hindcast data to look at every single transect and compute sort of a wave climatology from it. And this shows that these summer narrow beaches, their summer waves are much more likely to be from the south than these ones in the sort of winter conditions where, the winter narrow conditions where waves in the summer are coming from the northwest. And those are, in Northern California, we see a lot of wind waves coming off the northern Pacific, versus in Southern California, we see a lot of south swell. Okay, I won't talk about that. So, do we see variations in the seasonal cycles? And my answer is there seems to be a diversity in both the magnitude and the timing of the seasonal cycles and beaches. And spring and summer narrow beaches exist. Not only do they exist, they generally occur on south-facing beaches, especially in Southern California. So Google AI was wrong. They're not all winter narrow, summer wide, right? That's something that we've said over and over again. But we can find places where that doesn't occur. And the setting, both the geomorphic and the wave setting, seems to explain a lot of the variance in the data. So, in conclusion, there are a wide range of beach types in California. And beaches are responding to a whole bunch of different things that produce trends, time-dependent trends, events, and all kinds of cool things in seasonality. And the cool thing is that satellites are providing noisy but useful data for us to see these things. And we're coming up with, because we have this wonderful new data, we're coming up with these new tools to try to see the signals through that noise. We're really excited about continuing that into the future. So with that, I would like to acknowledge I had a tremendous amount of help from all these folks who not only gave great ideas and good edits and encouragement and all that good stuff, but are also very good friends. And I want to thank you for your time, and hope we have a good afternoon. Yeah. You're supposed to give this to me. Oh, sorry. That's good water and shit. You're supposed to give me my mug. Okay. Sorry, he was supposed to present me with a mug to say thank you. I'm gonna make you totally embarrassed by having to stand in front of everyone.
And take it.
Yeah.
Yeah. Okay. Thank you. Yeah, I have a lot of questions, but I'll start with this one. I was thinking about the Klamath River changes with them opening up the dams, and what the projections are then for how, say, Gold Bluff Beach or those other beaches that have been accumulating are going to be affected over time.
Yeah, it's a really, really, really good question. And so, sorry, Ivana, for the water. Thanks for the mug, by the way. Good question. The question's about the Klamath. So I worked on the Elwha River in Washington, and there we saw 20 million cubic meters of sediment come into that coastal system and dramatically change the river mouth. That river mouth region, sort of the delta and coast around it, was historically eroding at about 1 meter per year because of the lack of sediment that it received because of the dams. Dam removal, and we have a couple papers on this. And primarily there, the dams were holding back a lot of the coarse sediment. In the Klamath, the dams are so far upstream that they capture very little of the coarse sediment load that's provided by the river. So it's really kind of an inverse of that. They captured a tremendous amount of fine sediment, and one of the bigger concerns there is the release of fine sediment and the sort of ecological implications of that fine sediment sort of filling in nooks and crannies in the channel, potentially, reducing oxygen levels, all kinds of things like that, and then also causing sedimentation in the estuary river mouth region, but not the beach so much. The idea is that that fine grain sediment, so silt and clay, when it hits the ocean waters, is going to be fairly mobile and be carried off to the inner to outer continental shelf. It just doesn't stick around the beach, right? If you threw a bunch of silt on the beach, you'd see a little plume, and then it would probably never end up on the beach, right? It'd go elsewhere. It's too energetic to be around. So there at the Klamath, sorry, long answer. The Klamath, we don't expect a major change in the coarse sediment load of that river because most of that coarse sediment is being generated by the lower watershed, where the landscape is much steeper and providing a lot more coarse sediment. And that's where all the placer mining and all the placer mining, so I didn't know this until I did this paper. The Klamath was the second largest gold mining region in the 1800s in California. No clue. I guess I kind of knew it a little bit, but if you start looking at the data, they hydraulically mined all over the place in that landscape. And so just like we saw the sediment wave come into the Central Valley and into the San Francisco Bay from gold mining, I think that's exactly why we see the Klamath. So anyway, sorry, long story. Sorry, what's that?
Well, now I'm wondering, because you said that was the sediment wave was tracked from 1880, right? And that beach started to, so I mean, is that the cause?
So what we say in the paper is that, and I'll repeat here reasonably well, is that it's certainly, that beach was formed since the 1870s, 1880s, when we have some of our first map, and our historic records go back into the 1830s and 40s and stuff, our written records, and then the language obviously goes back generations and generations and generations, so that understanding is there too. That wave of sediment came in, and it came in apparently through a number of ways. There's evidence that in the maps of other waves coming through. So the wave that we saw most recently, there were probably 3 or 4 of them over, the 150 plus years. And one of the things that we see in the watershed is the Klamath watershed. There's documented gravel bars that have they're gravel bars where they documented significant amounts of sediment accumulating and then being released in that watershed over time. And so we certainly see that very clearly right before the sediment wave came through to the coast that we monitored. And so during the 60s and 70s, that big sediment wave was coming through, presumably flushed in by the 1964-65 floods that that basically washed out, totally changed the Eel River and the Mad River and the Klamath River, and that caused a lot of gravel accumulation in the main stem channel, and just took decades for that to work out to the coast. It was built up in the early 80s. It was all built up in the estuary where we saw that really wide river mouth, and then the waves just started eating it and transporting it down coast. So these sort of multi-decadal sediment waves moving through systems is what I think we're seeing. Sorry, this is totally a long answer for does that help?
Yeah, that was fun. Thank you.
Yeah, absolutely. Yeah.
So I remember you mentioning how you're able to use that kind of wave of sediment to track the sources and sinks of where sediment's ending up. And I remember you mentioning mineralogy, and could you just touch upon how you're using mineralogy to supplement those waves of sediment as well?
I am not.
You're not, okay.
But this actually gets to the question you asked, and I didn't answer. And that is, can we identify the causes of the sediment wave, especially in the Klamath, better? And I think mineralogy and stratigraphy would really teach us a lot. And if students, if anyone, if the geologists I knew were interested in working with a national park and, backhoeing a big trench across that really long beach and like really investigating and seeing and making sure we can characterize the source of those sediments and how they were laid down over time, and does it make sense? Can we do any kinds of dating or on any materials in there? That I think would be, but it's tough. I know it's tough, but I think there's potential to add to the story in terms of our hypothesis about were there a couple of these waves that occurred? Is there any evidence for any beach that was there hundreds of years ago? I mean, all the records we've looked at suggest no, but if we really looked at that sediment, mineralogy would be one of many. Yeah. Yeah, let's do it. Northern California for a summer? Let's go. I think there's a lot of potential there, and I'm reaching out to some, and specifically the last sentence of that paper in the abstract is a call to my geology colleagues, like, hey, let's go look and see if we can verify this and learn more about what happened here, because I think geologic evidence is the next place to go. So you're right on in your question, like answering that story is really now for the folks on the ground who can get in there and understand the deposits that are there, shallow, deep, all over, and try to put that story together for when that beach, came about.
Does one beach make it more difficult to analyze than another, like something that's pretty laminar flow or something with not a lot of flow? Is it easier to take a core out and see, like, oh, this happened on this year and this happened on this year, but something more that has like more wave action, like a beach in Monterey Bay, like would that be more difficult?
That's a great question. I'm going to talk to my geologist friend here who knows more about this. I mean, yes. Yeah, of course. I mean, what you really, right, in these types of studies, you want to both be able to see differences, right? What your first thought was, this is really hard. It is really hard unless you're in, some of the better places to do these types of studies are where big events occur that are sort of a different scale from what has been going on. So like a marsh, a muddy marsh, right? Picture out here, right? Big tsunami comes through, rips up beach sand and splays it all over the place. Whoa, there's a sand layer in here. What is that? That's an example of something very easy to see. Beaches, right, are just reworked and reworked and reworked and reworked, and certainly have, they'll preserve some sense of what the slope may have been, maybe some changes in mineralogy, but that can just be swash processes, right? So they're a little more complicated. I don't know if that helps, but you're fine with it? But yeah, I think they are fairly complicated, but in general, yeah. I mean, it'd be really interesting in the grain sizes and minerals. Right. Yes. Right. Right. Yeah. Yeah. Right. Mud's sticky. Right. Wet mud is really nice and sticky, and you're like, right. That's easy. Like you take a box core, a core through mud, and it's gonna stick together. It's sand. You vibrocore sand, and it can shake and destroy some of those features. And so yeah, I like to stay in the mud when I'm trying to do those types of studies. Sand's a little harder. Yeah, sorry, went way over.
Yeah. Of course, we're going to talk more about
Yes.
but this is really cool stuff. I mean, your paper, I hope it gets accepted and published.
Should be. It should have been 70 days ago, but who's counting how long the reviewer is taking to
No.
respond?
Good luck with that.
Yeah.
And of course, you can take the paper in any direction. You can also take it forward, so you can start you're working with Vitezek, so you can start making prediction for future trends in shoreline position, right? I mean, I guess that's the next step.
Yeah.
But one question that you asked earlier, and I have for you is, so not all beaches come with the same flavor. There are beaches that are result of modern river input.
Yeah.
Some other from coastal erosion.
Yeah.
So it depends on what type of rocks you're eroding. So is that what you were alluding when you were talking about Point Reyes? Because much of the pebbly beaches there are actually, coming from like Point Reyes, Point Reyes, Point Lobos.
Mm-hmm.
All these cobbly beaches are actually, the pebbles are coming from Eocene units. So is that what you're saying, that you see difference also related to the actual source of and grain size? And
I think we see changes because of the source, but we don't have a great grain size and mineralogy database to base that finding upon, and we need to build that. And for example, one of the things that we see, like in the Lost Coast, really steep beaches, not a lot of change. Sounds kind of gravelly to me, and I know.
But you have coastal geology maps.
Yes, right. So
those are already there. You can go over later.
Actually, I think it'd be really useful to get down there and spend a year walking this coast.
Why not?
And and just get a grain size every kilometer along this beach, right? And start and do that every year. Like maybe your grad students could do that. That's one thing that you could do.
But what I'm saying is that I bet that if you overlay also besides other things that I might, but if you overlay coastal geology map, you can start finding similarities between, where in Southern California, much of the sedimentary rocks that crop out are very fine grained.
Yep, absolutely.
So they don't provide any, real sediment to the beach. In Northern California, you do have all this pebbly beach. So I wonder whether you can do that. Just overlay a geological map. I mean, you do have it in GIS.
We do have it, and I haven't done that yet. It's a great idea.
I mean,
we've been trying to think about how we can jump in vans and drive them.
Well, that's for sure.
Measure sand.
That's for sure. But there's already one order of kind of a approach that you can do preliminarily, which is,
No,
Point Reyes is a great example. You got a Point Reyes formation, Pigeon Point formation. They're all, producing those pebbly beaches, which are actually kind of cool because they've been fossilized in time for 50 million years, and now they're being released back to the ocean.
Right. No, that's a good point. We haven't done that yet. And that's one of the layers we could add to our analysis. We haven't done it yet.
But the van sounds
I
great.
still want.
I like the van.
You're invited, by the way.
I like the van.
Because if you get down to it, one of the fundamental sort of properties of beaches, how they sort of change and how steep they are, is there's three general variables. It's wave height, wave period, and settling velocity or grain size.
Grain size.
Grain size, right? So grain size is of course, a grain steeper beaches, right? It's like fundamental. So like getting that,
Also, they
getting
become
that
more reflective, so you get feedback processes.
Right.
And yeah, no,
Right.
that's
Right.
what we study in our classes here.
Right, yeah.
So,
coarse, reflective beaches,
Yeah.
right? Yeah, absolutely. The dimensionless settling velocity. Omega. Anyway.
and then
yeah.
my second quick thing was about climate. I mean,
Yeah.
you were talking about wave region. I mean, it all makes sense. It's a
Yeah.
beautiful picture, where you see the offset between beaches being narrow during the winter as you go further north,
Yeah.
and vice versa. That all
Yeah.
makes. But there's also the actual weather that changes.
Yeah.
So you also have different, rain intensity. They come in different seasons. So I wonder whether you're also considering that aspect on top of the oceanography.
We only evaluated wave information, and the wave height and wave power has a very strong effect on those, the amount of excursion, the excursion distance, and the timing of those big waves has a big effect on the timing of the seasonal cycle. We didn't haven't analyzed weather data. We haven't looked at precip but certainly a huge gradient, right? And
That's
one of the ways that actually weather influences our data is just the presence of fog and clouds and stuff. And we get a lot less data in Northern California.
because of satellite.
Yeah, right, yeah. I mean, on average, we get about 1 image per
Yeah.
month in Northern California, and in San Diego, we get about 4 images per month,
Yeah.
right? And so we have to, and that's one of the reasons we went to a monthly sampling of the data. So weather's in the data, but not in the way you asked. But it was-
Different
yeah,
type of way.
Yeah, a different way.
All
Yeah.
right. Well, thank you.
Yeah.
All right. Thank you so much.
Sorry it went so late, folks. Is that clock right?
Finally, some good stuff.